Hello, today we're going to talk about free energy of dissolution. Okay, let's talk for a minute about enthalpy and entropy. Enthalpy is delta H. If you have a positive value of delta H, that is endothermic. If you have a negative value of delta H, that's exothermic. Exothermic processes tend to be thermodynamically favored. Now, if you remember, entropy is delta S, or just S. But for the most part, we're talking about delta S. Entropy for a system, if it's positive, that means you're getting more disorder, more disorganized. If it's negative, you will have less disorder. Positive tend to be more thermodynamically favorable. So exothermic and more disorder. Those are your more likely to be thermodynamically favorable processes. Okay, so let's review the process of solution formation. In order for something to dissolve, the intermolecular forces between the solute particles, so the solute-solute interactions, must break. The intermolecular forces between the solvent particles, so the solvent-solvent particles, must also break. And the intermolecular forces between the solute and the solvent must form. So you're breaking apart the solute particles, you're breaking apart the solvent particles, and they are forming new interactions between each other. Now let's relate that back to delta H and delta S. Breaking bonds is endothermic, so that means delta H is positive, so it's positive for both of those things. But when you form new bonds, that process is exothermic, so delta H is negative. But we can't just look at enthalpy when we're looking at the overall favorability or spontaneity of a particular process. So we also need to think about the delta S, the entropy. When you're breaking things apart, that tends to increase the disorder. So when you're breaking things into smaller pieces, you'll have more particles floating around, so more microstates are available, more disorganized. When you're forming new interactions, like the solute-solvent interactions, that's going to decrease the amount of disorder in the system, or a negative delta S. So this is what's going on here. Now, when you are looking at the spontaneity, you need to look at both of these things. Okay, so in order to get something to dissolve, it has to be thermodynamically favorable, unless you're going to put in work in some way, but then it wouldn't be a spontaneous process anymore. Remember, for it to be spontaneous, delta G is negative, and delta G is dependent on both the delta H and the temperature minus the temperature times the delta S. There we go. So Gibbs free energy is dependent on both the enthalpy and the entropy times the temperature. Therefore, remember that delta H is thermodynamically favorable when it's negative, when enthalpy is negative, and for entropy, we want it to be positive to be thermodynamically favorable. So effectively, these factors, the positive delta S and the negative delta H, have to outweigh the not favorable factors, the positive delta H's and the negative delta S's, which, if you have a substance that is dissolving, that is exactly what's happening. Okay, so questions like this might ask you about, what is making the process thermodynamically favorable. It would be the breaking of bonds, and the negative delta H from the forming of the new solute-solvent interactions. Now, which solution would have a greater entropy with all of the other factors remaining equal, and justify your answer? So for A, we have a saturated solution of cobalt hydroxide, and they gave us the KSP value. Remember, KSP is the substance. I'm just going to use a generic substance like this. It has to be dissolving from its solid form into the ions, whatever those ions happen to be. So the larger the KSP value, the more ions it forms. Okay. So now in this one, cobalt hydroxide, it's 5.92 times 10 to the negative 15th. Our second option is beryllium hydroxide. Its KSP is 6.92 times 10 to the 22nd. So the KSP for cobalt hydroxide is much, much larger. So that tells us, we want to know which one has the greater entropy. It's going to be A. A has the greater entropy because it's forming more particles that are separate in solution. Okay, it's splitting apart, breaking up the bonds between the metal ion and the non-metal ion, which in this case is cobalt and hydroxide. So because it has more ions, it has a greater entropy. Okay, for each of the following, choose the variable that will be more favorable in solution formation. So are we looking at weak or strong solvent intermolecular forces? Remember, when you are dissolving something, you have to break the solvent intermolecular forces, and breaking those bonds apart tends to be more favorable, so having weaker forces will make it more likely that the solution will dissolve. Same idea with the solvent intermolecular forces. You have to break them in order for the solid to dissolve in the solvent, so for it to be more favorable, we want weak intermolecular forces. Same thing for both of these, your delta H will be positive. So the weaker the bond is, the smaller the enthalpy involved with breaking those bonds. So weaker ones wind up being more favorable that way as well. Now for part C, weaker, strong solvent-solute intermolecular forces, we want those forces to form when a solution forms. So we want these attractions to be stronger. Again, because when forces are forming, your delta H is negative, and the stronger they are, the more negative it is. So that helps it become more favorable. Now, if we have an increase or decrease in entropy, of course, increasing entropy is more favorable because it's getting more disorganized. And then increase or decrease in enthalpy, we want enthalpy to decrease. We want it to be more exothermic overall, which is why we need the strong solute-solvent intermolecular forces.